Okay, so I am Daniel Varjas, and I am going to talk about our symmetry analysis tool QSymm. And part of the reason that this is here, that we developed it together with Anton, and also QSymm supports using quant systems, as I will demonstrate in this simple example. So what does QSymm do? So we very often face the problem that we want to know about the symmetries of the systems that we are investigating. So for example, you heard about Majorana wires that have particle hole symmetry, or quantum spin hole systems that have time reversal symmetry. And a lot of this analysis is kind of just doing a recipe, which can become quite complicated. So that's why we went through the trouble of automating it. So there are two core concepts in QSymm. One is Hamiltonian families, which you can think of as a Hamiltonian that depends on some free parameters. So for example, the bandwidth or the mass of the electron or the hopping parameters. And so we have the model class in QSymm that can store these symbolic representations of the Hamiltonian, and it works for continuum or K.P Hamiltonians or lattice Hamiltonians. And the other core concept are symmetries, and we support continuous symmetries such as spin conservation, spatial symmetries like rotations and reflections, and on-site symmetries such as time reversal or particle hole symmetry. And one way to go is, if you have a system defined by a Hamiltonian family, you may ask, what are the symmetries of this system? And we can automate this step completely and find all the symmetries of a system. And very often, if you write down some very simple K.P or tight binding model without even thinking of it, you make it extremely symmetric with lots of symmetries that you don't actually want. And so it is very good to be aware of this, and that's why it's nice to have such a tool. And the other way is when you have a given symmetry group and you want to construct Hamiltonians that respect this symmetry. And the Hamiltonian generator functionality does exactly this. It generates all the possible terms in a Hamiltonian that are compatible with the symmetry. When I say all possible, of course, there are infinitely many, but for example, for K.P models, you can specify what is the maximum power of K that you want to appear, or for lattice models, you can specify which types of hoppings do you want to include in the system, and then you get all the possible terms that can appear. Right, so if you want to read more details, you can look at the QSymm, read the docs where there are more example notebooks and tutorials. And also, if you are interested in how the algorithms work, you can read our paper. Okay, so let me show a very simple example. We are going to make a model of graphene in Quant and analyze its symmetries. So first I just import some things. So I import QSymm, I also import Quant, and in Quant QSymm there is the tools to convert between Quant and QSymm formats. And I import a couple of other things. These are mostly just for the outputs to look nicer, and also have to be careful that all the versions are correct and everything works together fine. Okay, so we make a very simple model of graphene on the honeycomb lattice. So we define a honeycomb lattice with the appropriate translation symmetries, make a quant builder out of this, add an on-site term, which is 0. So we have 0 on-site energy. And for the neighbors, we include a hopping, which will contain this free parameter T for the hopping strength. And then we plot the band structure, setting the hopping T equals 1. So this is one unit cell. You can imagine if you like start translating this with these 2 sites per unit cell, you get the honeycomb lattice and the familiar band structure with the Dirac points at the corners of the Brillouin zone. Okay, so we have the this model. So let's check out what symmetries it has. So first of all, we convert this quant builder, which we called bulk, because this is a bulk system with 2 translation invariants, with the 2 directions of translation invariance. We convert it to a QSymm model. So this is a Bloch model, which is used to store tight binding type Hamiltonians. We also have the model class, which can be used for K.P or even very general momentum dependence. Okay, so how does this look? Well, internally, this is a dictionary where every key specifies a hopping vector and the symbolic coefficient of this term. And with that comes a matrix, which is multiplied by the appropriate coefficient. So this is the hopping corresponding to this lattice vector. But to look at a nicer output, we can do printing in SymPy format. And now the Hamiltonian looks like this. So this is a 2x2 Hamiltonian because we have 2 sublattices on the honeycomb lattice. It is 0 on the diagonal because we had 0 for the on-site term. And these are the hopping terms. You see each term is multiplied by t, and these exponentials correspond to all the hoppings for all the nearest neighbor bonds. Written in a specific basis for the honeycomb lattice. Okay, so to find the symmetry group, we need to have an initial guess for the real space symmetry group, for which we guess it's the hexagonal group. You don't have to think too much about this because in 2D, there are 2 maximally symmetric point groups, the square and the hexagonal. And we conveniently have those predefined in QSymm.groups. And now we just call QSymm.symmetries with this Hamiltonian. We provide our guess, and we want the pretty output, and we want the full group returned. So what we get, I'm not going to show all the 48 symmetry elements, but it turns out that indeed this model has full hexagonal symmetry, including time reversal and chiral symmetry. So let's just look at only the generators now. So this group is generated by, this is an arbitrary choice for the generators, but for example, by a pi rotation, like a 2-fold rotation, a mirror with respect to the x-axis, and also a mirror with a 60-degree rotated axis. And besides that, we have chiral symmetry, which is the sublattice symmetry of graphene, and time reversal symmetry. Let's look more at this chiral symmetry. So with this list constructor, I'm just picking out the symmetry from the symmetry group, which is a chiral symmetry. And then I'm printing it. So indeed, I only have one of the chiral symmetries, and the explicit form of it looks like this. So what does it do to the Hamiltonian? Well, it acts with its unitary part from the left and the right, and it changes the sign of the Hamiltonian, it flips the energy. And we see that its unitary part is minus sigma z. And this object that we get out is this point group element object, which have convenience methods implemented. So for example, you can multiply them together, take powers of them, or have them act on a Hamiltonian to do exactly this kind of transformation. Okay, we also have a time reversal symmetry. We can have a look at that too. So that conjugates the Hamiltonian and reverses K, and it acts like minus identity. Okay, so let's do something that is often done to Graphene. Let's add a staggered Onsite term. And so for the staggered Onsite term, we just have a coefficient U and a sigma z. So this is 1 on one sublattice and -1 on the other sublattice. So this will also return a Bloch model, which I just described. We can simply add this to our previous model and look at what we get. Well, this is the same as before, except now on the diagonal we have U and -U for the two sublattices. And if we look at the symmetries of this new Hamiltonian, we find that now the chiral symmetry is missing from the generators. We still have time reversal symmetry, and something you might not have guessed before, we have a symmetry which is a twofold rotation combined with chiral symmetry. And this actually makes sense because a twofold rotation actually interchanges the two sublattices. So if I interchange the two sublattices and also flip the energy, then I'm back to the same place because I put opposite sign on-site energies on the two sublattices. So just to be sure, we check that there are no chiral type symmetries in the symmetry group. And as the last step, we can convert this model that we just constructed here back to a quant model. So for this, we have to provide some more information. So first of all, what types of sites do we have and how many orbitals are on each site? So this is specified as an ordered dict for n orbs. So this is just saying that there is an A sublattice with one orbital per site, and there is a B sublattice with one orbital per site. And we also have to provide the lattice vectors for the lattice. This we just take from the lattice that we used before to define the quant system. So these are just the two lattice vectors from there. And we also need to provide the coordinates of the atoms. These are again just taken from the quant predefined honeycomb lattice that we already used. And now we can call the model to builder function, which is in quant QSymm, which with all this information will convert this new Hamiltonian back into a quant builder. And now we can use wraparound in quant to calculate the 2D band structure again. So if I set the on-site potential to 0, then nothing should change. So I get back exactly the same familiar band structure with the Dirac cones as I had before. And if I set U to be non-zero, for example, if I set it to 1, then you see that the gap is opened at all these Dirac points. as expected. So this shows that the Dirac points are really reliant on not having a staggered potential in graphene, and to have this sublattice symmetry. So that's this simple example I wanted to show you. And if you want to work on it to familiarize yourself with QSymm at home, I made an exercise where you can look at the continuum model for the Majorana wire that and that we looked at in the previous session, and do a similar symmetry analysis on that case. Okay, thank you.